Yeah, before we move to the next question, let's do some summary here. All right. Through this simple example, I like to convey one point. Yeah. So that is the key to solve this problem is this. Okay. Yeah. Discover some special properties. Right? Here, many of you can discover this property easily, yeah, because, yeah, so you add up all the points, all the dots, number of dots. So then, use some complementary relationship. Yeah. Visible, invisible, there is a complementary relationship. Yeah. So then you take advantage of that property so you can find the answer. All right. Yeah. So now let's look at the second example. Look at a chessboard. How many squares of different sizes can you find along the grid of a chessboard? 8x8 chessboard. There are many different squares, right? Yeah. Look at that. So here, this is a square, right? Okay. How about this one? Another square, okay? Then another square, many different squares. Here we need to do the counting. Count all possible squares you can find in this chessboard, okay? Along the grid, right? Yeah. So think about, yeah, what method or what property, you need to use here, okay? Yeah. Yeah. Think about different sizes, how to handle the squares of different sizes. What? Yeah. So yeah. Diagonal. Do you want di diangle? Yeah. What? Going have sizes one by one. Yeah. Good. Yeah. So Madison. Yeah. Your observation is correct. Smallest size 1 by 1. The largest size 8 by 8. That's a good progress. That's good progress. All right. Diagonal. All right. Yeah. So right. So here you view using the diagonal way to view. Yeah. All right. Yeah. Because for each question, we may have different views. All right. Different views. Yeah. Some of the views could result easier solutions, and some of the views could result in harder solutions. Yeah. All right. Yes. Okay. Yeah. All right. Yeah. So let's do the thinking try to solve it using Madison's suggestion. All right, Madison's suggestion. All right, yeah. If you start a corner, oh yeah, corner, then progress across it will, yeah, right, yeah, corner. But if you use that way, try to cover all the possible squares. All right, don't just count the diagonal squares. Yeah, so Dakota, so when you use your diagonal way, do not miss some of the squares. All right, yeah. Yes, that's the reason. That's because when I see your diagonal, this word, I realize you may miss some of the non-diagonal squares. Yeah. So that view, that means this view is not the best view. Okay, the diagonal view is not the best view. Horizontal view, vertical view, better, because you can cover all the possible squares. All right, yeah. But here I like to follow the suggestion by Madison's suggestion. Yeah, so let's do it, because there are different sizes. Yeah. And 1 by 1 through 8 by 8. Okay, yeah. And when we start, here I like to convey one commonly used thinking way. Yeah. 8 by 8, that's the easiest size to be counted. Easiest size. All right, yeah, so let's count. All right, case 1, let's count 8 by 8 squares. How many? So that number Madison already put there. 1, right? Yeah, so that's 1. Yeah. Subtotal, yeah, we can, subtotal 1. Yeah, here I just wrote the number 1. All right, then 7 by 7. How many? Okay, yeah, let me look at Madison's input. Overlapping, yeah, overlapping allowed, yeah, allowed. So the only thing we need, we care about, it's a square. Okay, yeah, it's a square. Yeah, so overlapping squares, that's fine. Yeah, no problem. All right, 7 by 7, 4. Yeah, all right, so here 7 by 7. Yeah, because 8 by 8, that's easy. 7 by 7, look at the horizontal. How many 7 by 7 we can have? Horizontal, all right, 7, this is 1, 7 by 7 square. Then another one, 7 by 7. So horizontally, you have 2, right? Yeah. Horizontal, yeah. So this direction, horizontal. Vertical, you have 1, you have 2, right? Yeah. You have 1 vertical here, you have 2 vertical here. Okay. So horizontal, you have 2 different cases. Vertical, you have 2 different cases. So now 2 by 2. The total number 2 by 2. So that's how the number 4 comes from. All right? Yeah, comes from. So that's 4. All right? Then next one, you notice some rule, right? 6 by 6. Number of squares in the size 6 by 6 sizes. Horizontal 3, right? Vertical 3, 3 by 3, 3 square. Okay, yeah. Now you can do the analogy for all the possible sizes. 5 by 5, number 4 by 4, right? Because you look at horizontal possibilities, vertical possibilities, then 2 dimensions, multiplication. Okay, multiplication. Yeah. All right. Next case, 4 by 5, size. Yeah. Here, this column, the first column, size. Okay, or size. All right. This column, the number. Okay. Yeah. 5 by 5. All right. 3 by 3 size, and the number 6 by 6, 6 squared. Okay. Yeah. 2 by 2, 7 by 7. The last case, 1 by 1 size, the number 8 by 8. How about that? Okay. All right. Yes. Yeah. Madison noticed the inverse. Good. Yes. Yeah. Yeah. Right. Inverse. All right. Yeah. So that rule. So you need to observe some special rule here. All right. Yeah. So now the total answer. Yeah. So you can calculate the answer 1 square plus 2 square plus 3 square dot dot dot. So the last one 8 square. Okay. Yeah. So then you can find that number. Here I do not do that. Yeah. So I allow you use calculator. Okay. I allow you use calculator. Okay. Yeah. So we can get that answer. Yeah. Now the summary. Calculators on, allowed. Calculators allowed on the exam. Yeah. And also allowed. So regular calculators and online calculator, even online calculators are allowed. I hope you know some online calculators, because the calculators, regular calculators on your cell phones, those may not be very powerful. Think about some of the operations. I'm afraid you cannot do, like log, square root, roots, sine, cosine, yeah. But online calculators, so you can find some powerful online calculators, yeah. All allowed. Okay, yeah. All right. Here, I like to do the summary. Yeah, after this question, so after you see the solution here, I want to convey one point here. So we are given data. So the chessboard, the number of squares on the chessboard, that's the data we have. And we need to process the given data to find some answer. All right. So here, in the real world, we are given initial data. Okay, we are given initial data, all different kinds of initial data. And then we need to do data processing. Based on the requirements, we need to do certain data processing. Okay, yeah. So when we do data processing, there is one special consideration here. You can see in this example, that is organize the given data. Organize the given data. The original data may not be organized. It's quite randomly given, the original data. Okay, yeah. But sometimes you need to do some processing to make your data organized. So in this example, we can see we organize our data in different sizes. Okay, in different sizes. At the beginning, we do not view the given data in different sizes, right? Yes. So that's the reason, when, let me see, Madison, right? When Madison, gave us suggestion. His suggestion, actually, he recommends some special way to organize the data by sizes. Organize the data by sizes. That's an important observation. Very important observation. So then we follow that direction. We organize our data in different sizes. The reason here we can enjoy the benefit of that data organization step, because for each size, the counting is much easier. Okay? For each individual size, the counting is much easier. Okay, so we can do it quickly. Yeah. Then we put them together, we add it up, so all the sizes, very easy. But you need to make that step first. You need to make that step first. Data organization step first. All right? Yeah. So here you can see, although these two examples are quite special, but there are some common principles, common ways that we use in general problem solving. Data organization, that's a common approach that we need to use in our real world computing problem solving. Okay? And the first one, discover some special properties. Probably most of the time we need to discover some special properties. Yeah. The question is how to discover, right? That's another question. How to discover special properties. Yeah. So later, when we have more examples, I will give you some suggestions how to discover different properties. Okay. All right. Yeah. So we complete our topic 8.1. Yeah. Just these two examples. Yeah. Yeah. Total 204. I do not know by myself. I need to, do it on paper. Yeah. Yeah. So then, there is, actually, when we do it on paper, we get some number. But how do you know your answer is correct or not, right? When you do the calculation, you try your best. But the question is, how do you know your answer is correct? Think about that, right? Yeah. And in order to answer the question, make sure your answer is really correct. Although you can do the calculation a few times, but another better way is try to calculate the same formula in different ways. Yeah. Can you find an example that is 1 squared plus 2 squared plus n squared? Yeah. Because there is a formula calculate 1 squared plus 2 squared dot 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 plus n squared formula, right? Yeah. Because when you learn the discrete math, there is this formula, right? Yeah. As I remember, 1/6 times n plus 1 times 2n plus 1. Something like that. Yeah. If this formula is correct, let's plug in 1/6. So here our n is 8, right? 8 times 9 times 17, right? Yeah. So 3, 4, right? Yeah. 17, 51, 4. Good. Yeah. 204. Good. The same as the one Dakota give us. Yeah. But here I calculate in different way. Yeah. Okay. I calculate different. There, when we calculate the same formula in different ways, and they have the same result, then we have more confidence, right? It should be correct. Yeah. Yeah, because two different ways, it's very hard. You do it wrong in two different ways, but you get two same wrong number. How about that? Yeah. What is that formula called? All right. Yeah, good. Yeah. I need a little more space. Yeah. All right. Because this slide, I use up all the space. Yeah. Let me borrow the space here. Yeah. The formula. All right. Yeah. Okay. Yeah. Since you asked me the formula, yeah. Well, I still keep this one. Yeah. Because later I will post this notes. You can download my, annotated notes later. Yeah. The formula. Yeah. For Dakota, for your question, I like to start from the first formula that everybody knows. All right, that's a simple formula. That's 1 plus 2 plus 3, the consecutive numbers through n. I believe all of you know this formula. No, yeah. That's 1/2 n times n plus 1, right? Yeah. All right. Then I believe in your discrete math. Yeah, the prerequisite for this course, discrete math 3000. Yeah, if you still keep that textbook, or you can, all your notes, you can go back and check it. Yeah, the formula should be. Yeah, we need to find this for. We need this formula. Okay, n squared. Then, yeah, it's much more complicated. To find this formula, it's much more complicated. Yeah, but the answer is 1/6 times n plus 1. But the last factor is 2n plus 1. 2n plus 1. So this is the formula. Okay? Yeah? Yeah. Yeah. So here, I believe it's correct. So that's why I plug in the numbers. We got the same answer. So I feel it is correct. Okay. All right. If this had been a coding project, would we have gotten full credit had we do either way? Yes. Yeah. Coding project, yeah, either way, yeah, if it's correct, if your answer is correct, okay, yeah. Yeah, because the coding project, you will run a for loop, right, to do the calculation. Yeah, that's fine. So for the coding project, I assume you have two different ways to do the calc. The first way, just to write a for loop. So add up the sum of all these consecutive squares. Another one using this formula, 1/6 times n times, plug in to find the answer, both correct. Okay, both correct. And actually the first way, so actually the formula way is much faster. The formula way is much faster than your for loop way. So when you do the coding way, there is a for loop way. For loop way and the formula way. And the formula way is much faster than the for loop way. Yeah. Okay. Yeah. So that's why if it's possible, we always try to discover some formula. But sometimes the formula may not be available, so we have to take the loop way. Okay. If the formula is available, we always pick the formula way because we can find the answer much faster. Okay. Later, we will have another problem with the similar situation. That's the Fibonacci numbers. Fibonacci numbers, you can calculate the Fibonacci numbers using the for loop way. But there is a formula for the Fibonacci numbers. So you can also calculate Fibonacci numbers using the formula way. How about that? Okay, yeah. But that's a later topic, our module 3 topic. Okay. All right, yeah. So already 7:30, so I need to move to the next topic. All right. Oh, I know, yeah, before I move to next topic, I noticed there is another question. You know, some student asked another question. I didn't give the response. So let me, yeah, I missed that. But I noticed that. Oh, yeah, let me check it. Okay. Yeah. Yeah, I saw this right. Yeah, I saw this from Jeanette. Yeah, from Jeanette. Would the pattern hold true for 3D or ND? Good. That's a really good question. The answer is yes. The pattern hold for even, yeah, not just 3D, ND dimensions. Yeah, that's a really, deeper question. Yeah, I like it. I like it. N dimension. Even you can push it to the n dimensional case. Yeah, because not many people can imagine n dimensional case, right? How many of you can imagine n dimensional case, right? It's hard, right? Yeah, but Jeanette. So yeah, yeah, from from her response, yeah. I'm not, yeah, I guess, yeah. If I'm wrong, just correct me. Yeah, Jeanette, yeah.
I do work beyond two-dimensional space. That's why I was asking.
Right, great. Yeah, because this question very deep, yeah, very deep. Yeah,
Is there a formula for n dimensions?
just product of, you know, product of all the numbers for, all the dimensions. Yeah, straightforward multiplication.
Thank you.
Yeah, right. Good. All right, yes. All right, yeah, let's move on. Yeah. Yes. For most of you, if you can imagine 3D, that's already super, Yeah, 3D. It's hard to imagine. Yeah, but sometimes we need to consider n-dimensional. Now, here, yeah, let me just say a few more words, because you mentioned that. I like to, talk about n-dimensional case, because many of you may feel why we need to consider high dimensional case if the dimension number is higher than 3, right? Because in our real world, can you imagine anything has dimension higher than 3, right? Yeah, it's hard, right? Yeah, good. Yes, you have a lot of background. Yeah. All right. Yeah. Yeah. So, yeah. But actually, we may encounter many data processing with much higher dimension. Yeah, not just 2 or 3. It could be 100, 1,000, very high dimensional data processing. That's possible. Yeah. The situation is just like this. Yeah. Because when we do scientific experiments, in order to make some very complicated scientific experiments, there are many control factors, right? Yeah, because you need to adjust, temperature, many different things, many different factors you need to consider. Each factor, we use one dimension to represent it. If you have 100 factors, you need to use 100 dimensions. In that way, you need to handle multi or high dimensional data. Yeah, high dimensional data. Okay. Yeah. So Even if you cannot visualize, yeah, it's because people, it's hard to visualize 100-dimensional data, right? How can you visualize in your mind? How can you visualize? Nobody can visualize it. Yeah. But we just treat it as formula. Yeah. Treat it as formula, 100 different dimensions. Can we use a formula to represent 100-dimensional data? Yes, we can. We can. Yeah. So here, for example, x1, the first dimension, x2, second dimensional, and so on. x100, that's this is a 100-dimensional representation as a vector, as a 100-dimensional vector. Yeah, we can represent it. All right. Yeah. Anyway, yeah, let me just stop here. Yeah. So let's continue our next topic. All right. Description of an algorithm. Now we need to get to the coding part. Yeah. 8.1, we focus on the problem solving part. Yeah. Because we need to find a solution first. Given a computing problem, we need to find a solution first. But 8.2, after we have a solution, we need to implement. We need to write a program to implement our algorithm. So we look at that topic, description of an algorithm. Okay, all right, yeah. So first, the goal, find a solution for a computing problem. Yeah, so that's the general goal for this course. Yeah. After the training of this algorithm course, then when we go to the real world, we need to find a solution for a computing problem. Here, I use this general expression, computing problem, to represent, the general, real world problems. It could be, for example, it could be a sorting problem. You may ask me, what is a computing problem? Okay, what is a computing problem? Yeah. For example, sorting, sorting, giving an array. You need to sort this array in ascending order. That's a computing problem. Okay, that's a computing problem. General computing problem. Okay, yeah. All right, so then to find a solution, we need a precisely defined procedure to get the answer. Yeah. Step by step. Yeah. You need to know all the details to find your solution. Okay, first you have a general idea, so then you need to fix all the details before you can write a program. Okay, yeah. All right, step-by-step implementation details. Yeah, all right. And usually, yeah, sometimes when we work on a relatively complicated project, okay, yeah, we need to use flowchart to organize our thinking. Yeah. Otherwise, we may get lost, right? Too many steps, very complicated, so many different things we need to cover, yeah. In that situation, we may need to do the flow chart, try to organize our thinking clearly so we can, when we do the implementation, so we can implement it block by block, step by step. Yeah, so just like the diagram you see here. Yeah, all right. Then each step can be represented in code. Yeah, for the implementation, you need to implement each step in code. Yeah. All right. So then you will get a computer program. Okay. So then you use the tools, appropriate tools to generate your computer program. Okay. So right now, typically we use IDE. Okay. IDE. So that's integrated environment. Integrated development environment, IDE. Yeah, people call IDE. Okay. IDE. Integrated development environment, IDE. Yeah. Here, the reason I mention this because I noticed many students, they do not use IDE. They use the online compilers. Yeah. Yeah. Because when we write our programs, I noticed from my previous students, many students, they use online compilers. That's fine with me. That's fine with me. Online compilers. Yeah. Yeah. But if it's possible, I recommend you use IDE to write your code. Yeah. The reason is simple. When you use IDE, you can develop more complex projects. For online compilers, because usually you need to put everything in one file, right? If you have multiple files, it may not be convenient for online compilers. Yeah. So a better way is the IDE way. Yeah. But for this class, I do not force you to use IDE. So online compiler is still an option for you because for many students, yeah, so they feel hard to use IDEs. Yeah. But if it's possible, try your best to use IDEs. Okay. Yeah. But if you use online compilers, well, still fine. I will not take any point off. Yeah. And all my projects, all my two programming projects, you can use a single file way to complete it. So no problem. Yeah. Yeah. So you can complete the two projects using online compilers. Yeah. All right. Yeah. So now, summary, what is an algorithm? Yeah, based on our implement. So here we use the implementation point of view to look at the algorithm. Yeah. A sequence of instructions. Okay, so we need to generate a sequence of instructions to cover all the details of an algorithm. Yeah. And each instruction should be unambiguous. Yeah, should be clear. The meanings of everything should be very clear. Yeah, unambiguous. Yeah, and input data. So input data must be given, and the data must be legitimate. Yeah, yeah. So usually that means we need to do data validation. So there is a data validation step to make sure the input data is legitimate. Yeah. Then the output. Yeah. So the output, you need to follow the requirements. Yeah. So usually for a typical computing problem, usually think about in the business world. Yeah. You need to solve some particular computing problem for your customers. Okay? Yeah. Yeah. You need to find computing solutions for your customers. Okay? So your customers will provide you the requirements for the output. Requirements. You need to follow those requirements. Okay? For the output. Yeah. So it must be in the required format. Yeah. All right. Then another important factor in order to deliver a good solution for your customers, you need to really consider this execution time. Execution time is very important. How fast is your algorithm? That's extremely important for your customers. If it's too slow, your customers may not accept the solution, reject your solution because it's too slow. Okay, useless. Yeah, it could be possible. Yeah, so then you can see from this factor, you can see response time or performance or efficiency. Later we will, sometimes we use performance, sometimes we use efficiency of the algorithm. Very important. So for this class, we will spend a lot of time to improve the efficiency. Yeah. Yeah. Every time when we have an algorithm, we need to ask ourselves, can we improve it further? Can we improve it further, right? Is it the best solution we can find, right? Yeah, so that's all about efficiency, execution time, okay? Yeah, all right. In our part B, because today we will run out of time quickly today, so we cannot do part B. So I'd like to start the whole part B topic in our next meeting, next lecture, yeah, because it's a very big, important topic. Yeah. In part B, we will right, good, yeah, I will make comments later, yeah. So in part B, we will really do the comparison on two different algorithms on the same computing problem. One is very bad and one is very good. And you will see how big is the difference. So I like you to feel about it. How big is the difference? You know, two different solutions, one very slow, one very fast. Okay. And after that, we will do our first programming project. Part B, the part B topic, we will do our first programming project. Okay. All right. So now let me make comments on Dakota's question. Then are we gonna look at, oh yeah, that's the asymptotic notation. Big O of n, big O of n squared, right? We call this kind of special notation called asymptotic notations. Yeah, that's a big part of this class, asymptotic notation. That's our module 2 topic. In our module 2, we will study the, this abstract concept. This concept, very abstract, but it's important. Yeah, so because we will use this language after module 2, we will use this asymptotic notations a lot. Okay. All right. Yeah. So let me continue, finish the current topic first. All right. Then the execution time should be finite amount. That's the minimum requirement, right? Because it's impossible to have infinite amount with execution time. That means there is no termination of your program. You hit some infinite loop, no termination. The minimum requirement is your program must terminate at some point, okay? But you should not be satisfied with the finite amount. Yeah, because finite amount, it could be a very large number. Yeah, the response time could be a very large number. So we need to make sure we can make our algorithm the fastest. We will make the effort to get the fastest possible algorithm. Okay? Yeah. Yeah. Because the faster the algorithms, the minimum the computing cost. Now, computing time actually could be very expensive. Computing time. Yeah. So we want to make our algorithm the fastest possible. That's critical in the real world applications. Response time, it's critical. Okay? Yeah. So that's why that's our highest priority, to reduce the execution time as much as we can. Okay? Yeah. All right. Yeah. And you also, because you need to make your customers happy, right? So when you deliver a solution, the response time should be acceptable to your users, to your customers. Otherwise, you cannot get the money, right? Your customers may not pay for your solution, yeah, because your solution is too bad. Okay? Yeah. Yeah. So that's a very big deal here. All right? Yeah. All right. So we finish our 8.2. Yeah. Yeah. 8.3. So another example I want to show. Yeah. 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 But here, yeah, let me see. Yeah. Yeah. So it's a fake coin problem. It's from our textbook. Fake coin problem. All right. Yeah. So here, yeah, because I only have 9 minutes. So let me talk about the fake coin problem first. Yeah. So you can think about, yeah. All right. So here, the problem first. We have n greater than 2 identical looking coins. Yeah. So n number should be greater than 2. Yeah. N identical looking coins. So you cannot separate, you cannot find a lighter. Yeah. So here we assume a fake coin is lighter than a normal coin, than the genuine coin. But they have the same look, so you cannot find the fake one just by view of the looks. Okay? Yeah. And but you can use a 2-pan balance scale with no weights. Yes. No weights. Yeah. So you can only put coins on 2 sides of the balance scale. Okay? Yeah. No weights. Yeah. All right. One of the coin is a fake, lighter than the genuine coins. Yeah. Now, so that the challenging, the puzzle, this is a puzzle problem. Okay. Question: how to use the minimum number of weighings to find the fake coin? Minimum number of weighings to find the fake coin. Yeah. Yeah. Because we want to find the best solution. For the best solution, you need to use the minimum number of weighings, okay, to find the fake coin. Yeah. Here. How to solve this problem? Here, n is any number greater than 2. And it could be a large number. For example, n equals 100. Could be 100. Yeah. All right. Have it each time. Yeah, it's a, natural thinking. So I would say it's a natural thinking. Halve it, split in half. Yeah. Why split in half? Yeah, because you can put them on 2 sides of the balance scale. It's a natural thinking, but it may not be the best. Can you do better than that? Right? Better than that? Yeah. All right, yeah, okay, strategy. Yes, here, the strategy. When we solve most of our computing problems, especially those relatively hard problems, we need to apply certain strategies. Strategies are very important. Yeah. All right, so here, the first strategy. The first strategy, very simple, but you may not be aware of it, the strategy. So what's the strategy? Experiments for experience. Yeah, we need to do some experiments. Otherwise, we have no idea. We need to have some experience to inspire our thinking. Yeah. So, but when we do experiments, there is one commonly used strategy. Yeah. So that is work on some small problem sizes. Yeah. Here we treat n as the problem size. The problem size is n. Here, let's consider the smallest problem size. That's 3. Because n must be greater than 2. The smallest integer greater than 2, that's 3. Yeah. The question, can we solve the problem with the 3 coins, 3 identical looking coins? One of them is fake. The fake one is lighter than other coins. Can you use the minimum number of weighings to find the fake one? For example, one weighing, can you use one weighing to find a fake coin? N equals 3, just only one. Yes, right? Think about it. Because it's so easy. One weighing, given 3 identical looking coins. You know the fake one is lighter. You just use one weighing. You can find it, right? Yeah, yeah. Weigh 2, right? Pick, yeah, 2. If they are equal, the one not right. That's correct. Yeah, that's so easy. All right. Think about when n equals 4. Can you use one weighing? If 1 is impossible, can you use 2? For n equals 4. Yeah, 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 here. All right, because we run out of time, you just think about n equals 4 case. All right? Try to solve this problem for n equals 4. Okay? Yeah. Then next time we try to solve the whole problem. Okay? Next time on Thursday, we will solve the whole problem. Whole problem means for any n. For any n. Yeah. 1,000, 1 million. So we will find the minimum weighing number for n. Okay? All right. Yeah. So let me stop right here.